broad conceptual framework for this project. So we've done a bit of a deeper dive into the ecological thicket and developed like a more tailored workflow for this biome. So Andrew mentioned all these projects, and this is one of the projects that are mapping ecological condition. So it's a regional project called SBAP, Spatial Biodiversity Assessment, Planning and Prioritization. And the aim is to develop national spatial data sets on condition or degradation. Thicket only forms one piece of the larger puzzle. And we also have partners in Namibia, Mozambique, and Malawi. Sorry, I'm terrible at keeping the mic here. Okay, so I think you realize why we are doing this by now, so I don't have to repeat that. But we need these reliable condition data sets. So we're trying to establish a workflow that's reproducible across the biomes and can be tailored to the ecological processes in each. So how do we approach these assessments? I think Andrew gave a pretty good background on this, so I don't have to repeat that. But basically what they do is they take the veg map, they have national land cover data sets at different time steps or the current extent, and then you get a threat status with this red list of ecosystems. But the land cover maps don't differentiate the natural vegetation into further classes of condition. But these guidelines do provide some or two criteria for that, which focuses on the degradation of the abiotic environment, which would be soil erosion or so, and then the disruption to biotic processes. So our project is trying to collate and create, if we can't collate data, to do these assessments. So here's the overall workflow for this thicket project. It starts by understanding the functioning of the ecosystems, so the first step here on the left, understanding the functioning of the ecosystems, and then we move through the remote sensing, data prep, metric extraction, and modeling. And then ultimately we want to end up with these maps so that we can use that for the blue in national policy eventually. Thanks, Alistair. So this first step, we began aligning our work with the global ecosystem typology that Anisha Dharam will be speaking to you about later today. So this meant distinguishing different ecosystem functional groups, which are kind of equivalent to bioregions, because we can't do we can't generate a data set for every ecosystem in South Africa to assess condition with. So we focus on arid, mesic, valley, and dune thicket, and then the mosaics with all the other biomes, which is the tricky bit. But essentially, we want to make sure our methods are able to detect the disruption to these natural functionings of the systems. So I have like a little one page of each of these groups, just to make sure our work is grounded in what's actually the baseline. So then the second step is to acquire and clean the satellite data, which I use Google Earth Engine for. So we use Landsat time series, so that's at 30-meter resolution, and we have 38 years of data. So I just quickly wanted to mention here that traditional change detection methods have some limitations because they are based on categorical land cover classification. So they take time step 2, minus it from time step 1 basically, and then you get a change detection map like the one on the right. So this is very well suited for abrupt changes like clearing, because you can detect a clear NDVI reduction, for instance. But the utility diminishes where the vegetation cover responds gradually. So like overgrazing or browsing, unsustainable herbivory, past overutilization, And then we have to try and detect the symptoms and patterns associated with this past degradation, like Alistair mentioned this morning. And then the third step is to extract the NDVI from these time series. So NDVI is a calculation from the near-infrared and red bands of satellite data. And then we have this time series. So the picture on the left, or the figure, just shows you like monthly NDVI at each pixel. So I struggle with 3D thinking, so this helps me to navigate through this whole time series of data. And then on the right, it shows a wave pattern across every pixel because of seasonal vegetation change. So we use phenology in this project to detect vegetation in different states, or we're trying to at least. So this figure on the right shows the phenology metrics that we extract from each of these time series at every pixel. So you can extract things like start of the season, the length of the season, the amplitude, so basically productivity, the phase, so when is maximum greenest, when is the maximum, the greenest point, at what time of year. And then all of this together tells this kind of functional story that's happening at each pixel. And then the underlying assumption is that degraded pixels or behave differently over time to intact pixels. So they usually have shorter growing seasons because of grazing tolerant annual plants. And then they will have flatter curves, usually. And then you can also detect long-term anomalies of this, which could indicate legacy degradation. So Google Earth Engine supports pixel-level time series analysis with linear and non-linear regression. So linear trends are really cool to detect long-term trends, but they aren't super useful if the trends occurred before satellites started. So, and also where vegetation responds gradually. So that's where harmonic regression comes in. We fit these harmonic curves to the time series data. So this is an illustration of thicket vegetation in presumably 3 different states. These states are quite clear, but I just wanted to show you that the harmonic models kind of cut through the noise of the time series data. And then we extract those metrics from them. So this is an area close to the Darlington Dam, and I just wanted to show you an example of what we can do with these phenometrics. This is just for context, the veg map around there. So I'm going to focus on the Arid Thicket at the top and purposefully avoid the mosaic at the bottom. So these HSV maps are really cool, I think. So it's U, saturation, and value. It's to bring 3 different dimensions of these phenometrics together into one map. And then hopefully it highlights things that our eyes can't see. So the U would be the phase of this seasonal cycle. So when it's the greenest, or when it greens up. The saturation, so how dark it is the amplitude, so the strength of the seasonal cycle. So the brighter, more vivid colors usually corresponds to healthier vegetation, depending on in which vegetation you are. And then the value is the mean NDVI. So it combines those 3 things to visualize phenology better. So of course, so in the middle you might have seen it was fynbos. You can clearly see how it separates from the rest. And then in that red box at the top, and I just wanted to show you if you wanted to check. So it also starts to reveal these subtler patterns that we can't really see. So the darker parts are usually more degraded states. So the darker, desaturated, dull colors. But the point is to associate these patterns with known locations in the environment, so where we know what the condition is. And then we also have a lot of environmental data, hopefully, that we can use. And then we use experts to interpret this. So that's a fundamental part of this project, is that we have expert ecologists in each biome to make sure that we are interpreting all of this correctly. So that's where these training points come in. I've sent training points to Alistair Potts, Mike Powell, and Tony Palmer to score across the biome. So we just used random stratified sampling where I stratified by these bioregions. And then we have access to quite a bit of environmental layers, which we'll combine with those phenometrics with the training points to model with random forests. So it's just a machine learning algorithm that's really great and handling so much data and trying to reveal the patterns in them. So this is the step where I'm currently at, so I don't have results yet, but yeah, so the next step is to map. So we'll use these models to create the condition maps then at the end. And yeah, so those, it's like phenology maps. If anyone wants a live demonstration while you're here this week, like where you live or at your study site, just to see, it's really cool, the things that it reveals. You're welcome to come chat to me. I could just change the site and then it updates. So happy to come chat to me, and then I get to see the local interpretations of these patterns, which is important. So yeah, thank you. Thicket is our pilot for this whole project. So hopefully it works out here so that we can tailor it to the next biomes. Thank you.